I think we can start now. So, hello everybody, welcome back to our Wednesday seminar. So, today we have a speaker from INAF Italy. She is a postdoctoral postdoctoral researcher, Avinanda Chakraborty, and she will be telling us about the ongoing research in their group and being conducted by her. So, without any further ado, let's welcome Avinanda. So, you can start.
Okay, so thank you so much for the introduction. So hello everyone. Good afternoon. I'm Avinanda Chakraborty. As he mentioned that I'm a postdoctoral researcher in INAF Archetri in Florence, Italy. So first of all, I would like to thank the organizers for inviting me for this seminar, and especially my friend and colleague Sandra Jason for for considering me for this opportunity. And so, first of all, I would like to ask for apology for my bad voice. I'm not doing very well for the past few days, so that can affect my slides. But I'll try not to offend, not to disappoint you much. So that on that note, I'd like to start my presentation of today. So today I would like to talk about my ERIS, the work I'm doing here with ERIS observation of baryon cycle of a clumpy star-forming galaxy at cosmic noon. So I can assume that there will be people from several different expertise. So for that, and also because a lot of my time of postdoc I have invested in collecting data and doing all the reduction analysis. So I would like to go through all of them. First, I'd like to talk about the instrument I'm using, that is VLT ERIS, and then the method I have used for observation, that is integral field spectroscopy, IFS, and then I have done the data reduction and analysis, and lastly I have I would like to talk about the results and conclusion I have found. Let's start with the VLT telescope. This is a very large telescope. Is basically a 4-unit telescope with each 8.2 meter. This is an optical infrared telescope at Chile, Paranal, and I have used the ERIS, which is a new generation adaptive optics assisted instrument installed in the 4th unit of VLT. So ERIS basically combines adaptive optics with imaging and spectroscopy, and it is designed for high resolution studies of galaxies, stars, and exoplanets. So this is basically like the ERIS instrument installed in the Unit 4 telescope of VLT. So what is integral field spectroscopy? So we know the spectroscopy and we know the imaging separately, but this integral field spectroscopy which combines the spectroscopy and imaging. So let us understand this from this image. So what we see from a telescope is a 2D image, and then basically it is split into different slice. Then all the slices are passed through the spectrograph, and then it gets the spectral distortion. So basically, for a 2D image, what we saw initially, now it's no more 2D. We are actually having the spectral distortion, which in the wavelength axis, which means like it is no more a 2D image, we are actually seeing a 3D image. So basically, for a single pixel of that image, we are getting image as well as a spectrum, full spectrum for all the pixels present in the image. And so for ERIS, the newly installed spectrograph which I use is PFER. Okay. So now my work is, so I'm part of this ERIS GTO program. This is Guaranteed Time Observation Program of baryon cycle in star forming galaxies at cosmic noon. The PI is my PI, Francesco Belfiore, here in Archetri. And so the idea of this program is to search for star forming galaxies at cosmic noon. So cosmic noon is basically a period between redshift 1 and 3, which peaks at redshift 2, and this is called cosmic noon because we expect the most star formation in a galaxy in this time. So the plan is to find the galaxies, star forming galaxies and cosmic noon, and shed the light on how the baryon cycle drives disk assembly and bulge growth in that particular star forming galaxies, basically detecting different emission lines and try to get the star formation history of that um, galaxy. So I have done work on several galaxies, but for this work, I'll be only talking about this particular galaxy. Why? Because this is the most beautiful image we have found so far in our survey GTO program. It has this is a galaxy ZC40 at redshift 2.19, and as we can see, it has clumpy ring-like structures with many clumps. And as I already told, that it's a star-forming galaxy at cosmic noon. And for your information, that the center, there is nothing in this galaxy, only the clumps around like a ring. And this is a O3 emission line image that we have found just from the data cube, the 3D data cube, which has, like, as I just told, from the IFS, which has like two spatial axes and one spectral dimension. That's why we are not calling it as 2D, we are calling it as the 3D cube, which is an output from integral field spectroscopy. Okay, so now let us talk about the data. So we have used 3-band data. So basically this is a NIR near infrared instrument ERIS, and we have used 3 different data observations. And so this is H band, K band, and J band. So except for the K band, the H band and J band are from this ERIS GTO program of Francesco Belfiore. And the K-band data we have got from our collaborator Natasha in MPE team. So unfortunately, without their permission, I'll not be able to show the results of the K-band. I have to stick to this H-band and J-band data results. So what is the importance of showing this slide? So these 6 OBs, these are very technical terms. OB stands for object observing blocks. So for the time being, let's just for simplify it, and let's just imagine that, let's just consider that I have 32 images of that galaxy in H band, and I have combined that using the ERIS pipeline to get a final data cube. So what is the importance of this 32 time observing? Because more the integration time, more the better the signal to noise ratio I get. Now, and this is the same with the J band data. I have also combined and got the data. Better with the so these are the integration total integration time for how long the observation has been done. So how do you combine data? So for that, you have to observe, because these galaxies are very faint, these are far away. So you cannot actually see a galaxy directly. So if you cannot see the galaxy from the telescope directly, so how do you going to combine it? Because there maybe, because these observations are done in different days, so probably there can be uh, like a offset from the telescope position, because no matter how accurate you want to be, you want to put the position, there should be manual or different like offsets will arise. So for those, we need to observe the PSF stars. So from the position of PSF stars, we have calculated the offset. So for each observation day, we have observed different PSF stars in several uh, in several separation, and then from their offset we extrapolated and estimated the offset of the observing exposure, and then we finally estimated the offset and then combined to get the single combined data with good SNR. And there's another importance of this PSF star is with that, by fitting this 2D Gaussian, I could also estimated the PSF of the observation, that is basically the spatial resolution of the observation. This another star is very important to observe with the observation is that is the telluric star. For one for to because these are, like as we know, this infrared optical are ground-based telescopes, so we need to correct for the atmospheric observation as well. So for that we have observed the telluric star as well and then corrected for the atmospheric observations too, and also the flux calibration as well. So finally, after calibrating the flux and get rid of the atmospheric observation by combining all the data exposures by correcting the offsets, I finally got my final Q for both H band and J band. So now let's come to the results finally. So what I did is I separated the galaxy into different clumps. These are the clumps mask we have used using a AI code, and then because to I mean it calculates the values and then it estimates the clumps. It's a very complicated code. I'm not going into the detail. So what we have found from this thing, this slide is, so we after separating after getting the individual clumps and then fitting the Gaussian line profile, we found that for O3 emission line, we are getting for the three of the brightest clumps, we are getting the asymptotic the asymmetric Gaussian profiles, not so it's not the single Gaussian, it's basically the two Gaussian profile. But this is only for the three brightest clumps, but not for all the other clumps. So here we saw that, so these clumps are a good fit by a single Gaussian. So we basically stacked all of them, and still we didn't see any feature that can fit a second, that can be a need with the second Gaussian. So that's why we are fitting with the single Gaussian. So for these three brightest clumps, we are getting that asymmetric Gaussian profile. And also similarly, with the K-band data, we also got that the H alpha also has this asymmetric Gaussian profile. What is the like importance of this asymmetric profile is, this is basically telling the presence of stellar feedback, which means that, and also it is telling that probably these different clumps are talking about different stellar evolution time. So these are not from this doesn't have the same stellar history, but this is just a hint. Similarly, we also found that from the H-band data that the several clumps has differ like the H beta emission as well. We also found the similar way we try to fit, but there is no, of course there will be no, because the H beta is very faint, and also there was a presence of strong skyline here, so it is contaminated by skyline. So after taking care with the skyline, what we tried to do is we finally estimated the H beta emission line, And also I would like to mention here that with the K-band data, we also for several clumps able to detect N2 as well. Why I'm mentioning this? Because this is the this can tell the importance of ERIS SPIFER. Because before that, there'll be no such observations with this H beta detected for the same galaxy in all these clumps. Okay, so after getting the emission line profile, we tried to estimate the emission line map. So for that, what we did, we used a customized Python code. What it does is basically it feeds the simultaneous Gaussian, calculates the uh, chi-square, lowest chi-square, and then uh, after calculating, it feeds the same Gaussian in all the pixels, and it's also smooth the using a smoothing Gaussian kernel. It's also smooth the image with the smoothing kernel size is 1 pixel. So after doing all these technical boring things, I could get a beautiful O3 emission line map of the galaxy, which shows that the O3 emission lines are pretty much coming from all the parts of the galaxy. Similarly, using the same code, I have also found a very beautiful H beta emission line map. And why it is important, I mean, we can see not like O3, but at least a lot of clumps are, we can get some at least amount of H beta from different clumps, at least a lot of clumps. Let's just consider that. So why it is important, as I first thing is, as I already told, that this galaxy has been observed and there are other works of with this galaxy by previous in the present in the literature. But what is the importance of this our observation is that we are the first one to detect H beta emission line from most of the clumps. Now, what is the importance? I mean, what is so special we have done by detecting H beta? Because H beta can also estimate, can use as an estimation of the dust present in the galaxy. So as I already told that we got also some nice images, nice maps of H alpha, but unfortunately I cannot show without the permission of the MPE group. So, and this H beta and H alpha and H beta ratio actually can use as an estimation of the dust. So this AV map for the timing, let's consider this is the estimation of dust present in the galaxy. So, and we can correct actually, because the H beta was detected in several places, we can correctly correct the extinction, dust extinction for our maps. So this is actually one of the, this is the O3 emission line extinction corrected map I'm showing from our results. So that was one of the most important results we have found for this work. Now let's go back to the J-band data, because I talked about the K-band and H-band data. So what the J-band data does, it's very noisy. It's not as good as the H-band data, but we could actually estimate it. The O2 emission line flux and fit the line profile, and we can see the doublet of O2 from here. And why it is important to estimate the O2, because it can estimate the so using the O2 line emission line flux, we can actually estimate the metallicity of the different clumps. And unfortunately the O2 is not detected in many clumps. Only 4 of the clumps we could actually estimate. So these are the most important slide. This is the most important slide of my work. So using all the line emission line, H alpha, H beta, O3, O2, and N2, we could estimate these are the properties like the star formation, and also the H alpha O3 velocity, ionized mass, and mass outflow rates different for different clumps of AZs, say 40. So this actually is saying, like, is actually supporting what I initially suspected, that these clumps are telling about different stellar evolution, talking about the different stellar evolution history. So it is actually talking, because the values are different. So this is one of our conclusion of this work, that the clumps are actually talking about different stellar history. So we could also estimate the electron density, metallicity, and ionization parameter using the O2 emission. But how to check the thing we are doing, because the H beta is contaminated by a skyline, so we can actually cross check this SFR value. If we can check it in a different way, you can measure it. For that, what we did is we took the help of JWST and HST image, and we combine it with the ERIS bands data and fitted the ACD. This is also an image I cannot show for the same reason. So we actually saw that after estimating the ACD and fitting the parameters, the output we extract, that is, one of them is stellar star formation rate, which is actually going well with our estimation. So this is kind of supporting our results. So that is my conclusion. That, so first of all, like, so that is that the conclusion is basically that the galaxy is having different stellar evolution history. um, Thank you.
Thank you for the nice talk. So, any questions? Yes, ma'am. Can you please come ahead?
Hi, I am Thaisa
So,
Stork-Bergman. And so this is a star-forming galaxy that you
yes,
are observing, right? So these mass outflow rates that you are getting are not from AGN, it's from the clumps of the
yes,
star-forming clumps. So it's
yes,
like supernova explosions. Is that the
yes, could
origin?
be.
Mhm.
Yeah, could
Okay.
be. It's not from the AGN. As I mentioned at the beginning, that there's nothing in the center, so there's no AGN in this galaxy.
Okay. Maybe I missed it. The star formation rate, you have these numbers? Star formation of 54. Okay. Thank you very much. And this is a survey of these galaxies, or
Yes,
this is,
yes,
and
yes.
it's not a special one, it's just one that you analyze it.
Yeah, that's like, we have planned to analyze a couple of galaxies, and this is the most interesting one we have found, because then, I mean, in a follow-up work, we have found, like, as you can see, there is a presence of an intruder. And so, but our Aries image is actually, if I can show you the image, it's actually ending here. So now we are planning to observe this particular thing, and then we can see if it's like, we can say more about it, like how the galaxy was formed. So that is like a follow-up work we are currently looking at.
Yeah, I'm just curious, comparison of, the imaging of ERIS with the imaging of JWST. Do you see too much difference? It's much better than the JWST, or what
So
is your impression?
basically, no, actually not, because Aries is like a rival of JWS survey, because they have similar kind of resolution, so you can easily compare with the JWST image.
So it's similar, you think? Yeah.
Yes.
Okay. Thank you very much.
Yeah, ma'am, please.
Thank you.
The object that is in the it's like a star or is another object lying up and
You mean this intruder?
you have the ring.
I have the
and
ring.
see,
Yes.
yes, and
Yeah.
then you have another object. It looks like a star. No, it's not in this image and in the other one.
Yeah, so basically, I mean, this is our ERIS image, and the intruder is at the edge. So, but the JWST of FOV,
That's image.
yeah, this
In that
one.
image.
Yeah, so this is, we are trying to look at it, could be a galaxy or a star. So, and that is our like a follow-up work, because in ERIS we didn't see it because the field of view is ending here, just here. So, but we can see like, if I just go back to this image, as you can see, there are some signal we are also getting from here. So we saw it from the spectra, maybe not clear from the image. So this actually could be like a star from where like the galaxy is getting, like if the star is ejecting and the galaxy is getting from that. So it could be, so that is our like a follow-up work. This is not done yet.
Which are the physical sides of this galaxy?
So
The physical size in kiloparsec.
this is in kiloparsec size, like,
How much I can see?
no, this is in like
The size,
kiloparsec scale.
Diameter of the galaxy.
the diameter of the galaxy.
Sorry,
Like the diameter of the galaxy.
yeah, that's what I'm saying. Like this is the diameter of the galaxy is like uh, I mean in kiloparsec scale, like is equivalent to
50 kiloparsec.
no.
Like,
What I'm trying to say is it's okay. So okay, I got it. So it's like 100 kiloparsec range.
Because there are ring galaxies, looks like this galaxy, and is the result of the interaction between a galaxy that passed through the other one. So maybe in this case, I thought that the other object maybe is another galaxy.
Yeah, could be possible. I mean, that's like we haven't looked at it. I mean, that is our like a future work.
Mm-hmm. And have you observed it in the infrared? Some observation in infrared?
Yeah, infrared
Searching
ERIS
for
is
gas, molecular cloud.
yeah, ERIS is infrared observation. So this is near infrared observation. So dust estimation, I have already done this.
Okay, thank you.
Thank you.
any more questions? No? Okay, then let's thank our speaker. Thank you very much.
Thank you so much.
Okay, see you guys next Wednesday. So